So, antenna, this is a huge subject or big subject. So here for our gate point of view, we will discuss only the concepts needed, and I am not going here to derive all the derivation part and all those things. So whatever equations we need directly, I will mention those things here. So we will read only the important concepts, because this is a big subject. Here we are having, suppose, a source. It is connected to a transmission line. This is a transmission line. So energy is propagated. Suppose if you want to transmit the energy in free space, then here we will connect a waveguide. Here we will connect a antenna. Here we will connect a antenna. This is the antenna part. So this is free space. This is free space. So if you want to transmit the energy in free space, we need an antenna. The basic principle is to make more efficient radiation. Transmission line dimensions are widened. That part is called antenna. So for more efficient radiation in free space, here if you observe, the transmission line is like this. Just I am widening the dimensions. For making wideration of that part, I am calling as antenna. Or there are plenty of definitions for antenna. So antenna is a metallic rod which is used for radiation purpose. So in different textbooks we have different definitions for antenna. But the basic purpose of an antenna is for radiation purpose, to radiate energy into free space. So that is the basic purpose of a antenna. So the basic purpose of antenna is for radiating energy. Into free space. This is the basic purpose of the antenna. So for example, we will see what are the different types of antennas we are using nowadays. So each antenna is for different applications. Suppose the basic antenna is dipole antenna. So the dipole antenna looks like this. Just it is a conducting part, just a conducting wire. So this is a basic dipole antenna. Loop antenna. A loop antenna looks like this, in the form of a loop, like this. Loop antenna. So here I am considering a square loop, or there is a circular loop also. Circular loop. Another antenna of this kind. Antenna in this shape. Antenna in this shape. It's called helix antenna. Another antenna like this. Like this, which is a pyramidal horn. Another antenna of this kind. a parabolic dish. So like this, we have different kinds of antenna. Just here I am giving the general antennas. So we will use what are the shapes, just to know the shape of the antenna. There are plenty of antennas. Here one more thing you have to point out is, each antenna has its own application. Each antenna has its own application. So these are some basic antennas. So we will discuss about dipole antenna. Dipole antenna. So the dipole antenna shape is like this. This is a feeding point having conductor carrying a current I. The length of the antenna is L. The length of the antenna is L. So directly it will radiate, it will carry current. This is the dipole antenna. So here a dipole antenna is shown in figure. Here a dipole antenna is shown having length L and carrying current I. Next one is Hertzian dipole. Hertzian dipole. What is Hertzian dipole is? Hertzian dipole means the length of the dipole antenna is very small. That is, L is equal to some small length dl. That is, if the length of the dipole antenna is very small, then the antenna is called Hertzian dipole antenna. So this Hertzian dipole is carrying a current I. A current I. So like this. This is x-axis. This is y-axis. This is z-axis. This is a small length I of Hertzian dipole carrying a current I. The length is dl. Then the infinitesimal current element is ideal. Current multiplied by the length is the infinitesimal current element. So due to this current element, what is the field generated at a point P? At a point P, what is the from any point on the current element at a particular distance r, what is the field intensity we have to calculate. This is about theta. This is theta. We have to calculate this length. This is P. So if you use general basic coordinate system concepts, this is phi. So we can solve this problem more easily in a cylindrical spherical coordinate system. We have to calculate what is the field at any point P due to this Hertzian dipole. Since the derivation is very big derivation, here I am not going for the derivation, just I am giving the what are the fields directly. So the electric field, so I am mentioning the electric field. The electric field at point P due to Cartesian dipole is ER. ER is equal to, because since it is a spherical coordinate, we have r theta phi, ER a theta a phi. ER is equal to 2 ideal by 4 pi epsilon into cos omega t dash by r square v, or phase velocity Vp, plus sin omega t dash by omega r cube. This is ER. So no need to remember these equations. E theta is given by I dl sin theta by 4 pi epsilon minus omega sin omega t dash by r Vp square plus cos omega t dash by r square Vp plus sin omega t dash by omega r cube, and E phi is equal to 0 you will get, where t dash is equal to t minus r by phase velocity. This is the retarded time, t dash. So these are the equations we will get. So we can calculate H theta and H phi also. If we calculate H field, the H field at the point P is given by HR you will get 0, H theta is equal to 0, and H phi you will get ideal sin theta by 4 pi minus omega sin omega t dash by r phase velocity plus cos omega t dash by r square. So you will get like this the E field and H field components. The important thing here is not the equations. No need to remember these equations at all. The important thing is, by observing these field equations, we can conclude that we have terms varying as 1 by r cube, 1 by r square, and 1 by r. 1 by r. Suppose here if you observe this term, it is varying with respect to 1 by r. If this term 1 by r square, similarly here this is 1 by r, 1 by r square, this is 1 by r cube. Similarly it is r square, it is varying with respect to r cube. So we have terms varying with respect to 1 by r cube, 1 by r square, and 1 by r. So these terms are important. So what is the term varying with respect to r cube? What is the term varying with respect to r square? What is the term varying with respect to r? So the first one is 1 by r cube term is called electrostatic field. Electrostatic field. This term dominates over other terms in a region very close to Cartesian dipole. This is one of the important statements. So this 1 by r cube term is called the electrostatic term, which is dominant very near to the antenna. The next one is this 1 by r square term. So 1 by r square term is called inductive field. It's called the inductive field. This term is important. This term is important only at a distance close to the antenna. Close to the antenna. So this term also dominant very near to the antenna. Therefore, we can say that 1 by r cube and 1 by r square terms are dominant at a near field. Dominant at a near field. The next one is 1 by r term. So this 1 by r term is called radiation term. This 1 by r term is called radiation term. Radiation term or radiation field or radiation field. Radiation field or far field. This is also called as far field. That is, this is dominant at a point very far from the current element. Very far from the current element. So these three terms are very important. So the first one is 1 by r cube term, which is called electrostatic field term, which is dominant very near to the antenna. And 1 by r square term, this is called inductive field. This is also dominant close to the antenna. So this 1 by r cube and 1 by r square terms are called or dominant at a near field, or these terms are also called as near field terms. And the 1 by r term is called radiation field, which is dominant at very far from the antenna. So the conclusion is, one by r cube term, which is known as electrostatic field, this is also called as near field. 1 by r square term, it is known as inductive field. Inductive field. This is also near field. 1 by r term, which is known as radiation field, far field. So in this particularly this antenna subject, for our examination point of view, we have to keep in mind a lot of statements and formulas. So here I am going in a way such that I am not discussing the theory elaborately. So whatever the important concepts for our examination we are discussing, since the subject is a huge subject. So if you consider this is the antenna, dipole antenna, I am considering a region like this. I am considering a region like this, which is near field. This is the antenna. This is a near field. and here I am considering somewhere else. This is far field. Far field somewhere here like this. Far field is like this. Far field. Another important point is the boundary between. So which is far field and which is near field. So the boundary between near and far zones. Far zones is given by the value r. Is given by the value r. Is given by the value r. R is equal to 2d square by lambda, which is very important formula. R is equal to 2d square by lambda. 2d square by lambda, where d is the largest dimension of the antenna. Where d is the largest dimension of the antenna.